Machine learning is often taught in the safety of a closed system. You take a pristine, heavily vetted dataset, feed it into a model, and measure the error. But engineering an intelligent agent to operate in dynamic, decision-making environments requires stripping away that safety net completely. Standard supervised learning relies entirely on a passive relationship with data. It takes a fixed input, variable x, and maps it to a predetermined expected output, variable y. The model learns to recognize patterns, but it has no agency over what patterns it gets to see. This diagram illustrates how reinforcement learning operates through continuous interaction. We discard the static dataset entirely. Instead, the learner is dropped into an environment and forced to generate its own data through direct, explicit engagement. This interactive loop relies on three specific mathematical variables. The agent observes its current situation, defined as the state, S. Based on that state, it executes an action, A. The environment responds by yielding a numerical reward, R. This feedback loop runs continuously. With each passing cycle, new information becomes available, and the agent uses those precise S, A, R coordinates to incrementally update its internal models. Pattern recognition is only the baseline. The engineering objective is to map a complete policy, a mathematical function, pi, that links any given state to an action that will maximize the expected sum of total rewards over the agent's lifespan. Because the agent generates its own data through interaction, it has absolute choice over what new information it seeks, and that choice creates a severe mathematical tension. We can isolate this tension using the K-armed bandit problem. Imagine a scenario where an agent has K different actions available to it, like pulling different levers on a slot machine. The catch is that the probabilistic reward function for every single lever is entirely unknown. After testing a few levers, the agent has a choice. It can execute an exploit strategy. This means analyzing its limited data and choosing the highest expected reward. The agent maximizes its immediate payoff, but it relies entirely on probability estimates that might be deeply flawed. Alternatively, it can choose to explore. The agent intentionally takes seemingly suboptimal actions, pulling levers at things are bad, specifically to gather fresh data. It sacrifices immediate payoff to improve the mathematical accuracy of its underlying reward models. The correct choice depends strictly on the time horizon. If an agent only has 5 moves left, exploitation is logical. But over an infinite horizon, rigorous exploration is mandatory. Otherwise, a string of early bad luck on a good action will cause the agent to converge prematurely on a terrible policy. You cannot hard-code a perfect path for an autonomous agent. Balancing this exploration versus exploitation dilemma is the foundational engineering challenge required to build a functioning RL system. Once we understand the interaction loop, we face a major architectural decision. Should an agent try to map out the complete physical rules of its world, or should it just memorize the expected value of its actions? This equation represents the first approach, model-based reinforcement learning. The agent attempts to explicitly calculate empirical models for the environment. It tracks exactly how the state transitions, T, and maps a deterministic reward function, R. Notice the +1 and plus magnitude of S. This is a Laplace correction, a smoothing technique to ensure we never estimate a zero probability while dividing by our observation counts. It works perfectly in small, discrete grids, and it fails completely at modern scales. To model those transition probabilities accurately, the equation requires multiple, repeated observations for every single state-action pair. If a robot is operating in a continuous physical space, the number of potential states is effectively infinite. Calculating an empirical model of the environment's physics becomes computationally impossible. To scale up, we have to bypass the environment's physics entirely. Instead of modeling how the world works, we pivot to model-free, value-based methods. We design an architecture that directly estimates the ultimate numerical value of taking a specific action in a specific state. The most prominent of these value-based approaches is Q-learning. Instead of learning transition models, the algorithm directly estimates the optimal state-action value function, a metric simply known as Q. This equation is the core engine of tabular Q-learning. It defines exactly how the agent updates its internal values after every single step. It breaks down into 3 distinct color-coded components: the current estimate, the learning rate alpha, and a temporal difference target. The learning rate, alpha, acts as a running average. It dictates how aggressively the agent should rewrite its current estimate based on new data, combining old predictions with fresh experience. This segment is the one-step look-ahead target. It takes the immediate reward just received, R, and adds the maximum discounted Q value it expects to get from the very next state. By subtracting the old estimate from this new look-ahead target, the entire formula functions as a continuous correction mechanism. The agent steps forward, measures the temporal difference between what it expected and what it actually observed, and corrects the record. But having a mathematical table of Q values is useless if the agent doesn't know how to act on it. To solve the exploration dilemma we established earlier, agents typically use an epsilon-greedy strategy. The math is simple. With probability 1 minus epsilon, each agent exploits the table, choosing the action with the highest recorded Q value. With probability epsilon, it ignores the table completely and explores a random action. Under fairly weak conditions, tabular Q learning mathematically guarantees convergence to an actual, optimal Q function. The only rigid requirement is that the epsilon-greedy strategy explores every possible action infinitely often. Mathematical guarantees of convergence on an infinite timeline do not translate to practical utility in the present. This diagram shows a controlled theoretical environment designed to test how efficiently the algorithm propagates value. It's a 10-step hallway. The agent starts at index 0 and receives a massive reward of plus 1,000 only upon reaching the final step, index 9. The first time the agent successfully traverses the entire hallway, it hits the reward. But because it updates based on a one-step look-ahead, it only updates the Q value for that final index from 0 to 1,000. The agent currently remains completely ignorant that steps 0 through 8 were good choices. The value hasn't reached them yet. To fix this, the agent has to run the hallway again and again. With each successive iteration loop, the Q values propagate backwards step by step, decaying by the discount factor with each shift. Quantitatively, it takes 10 full algorithmic loops for the starting position to even recognize the value of moving forward. Until that 10th run, the start position looks totally worthless. Now expand this mechanical limitation to a continuous, real-world environment. Storing and independently updating every single discrete state action coordinate in an exhaustive table demands an impossible amount of memory. As the state space grows, the computation required to propagate value backward scales exponentially. Tabular tracking cannot scale. If we want an agent to operate in continuous space, we need a radically different architecture to compress this matrix and approximate values across infinite states. The architectural upgrade is to replace the massive, inefficient discrete Q table with a function approximator, specifically a neural network. This visual represents deep Q learning. Instead of looking up exact coordinates in a database, we take the continuous state and action vectors, concatenate them, and pass them through the hidden layers of a neural network to output a single estimated Q value. By utilizing a neural network, we transform value estimation from a lookup task into a supervised regression problem. This equation shows the exact loss function required to train the network. It calculates the difference between the network's current prediction and the temporal difference target and squares it. This is known as the squared Bellman error. As the agent gathers experience, the neural network's internal weights continuously adjust through gradient descent, specifically optimizing to minimize this error metric over time. This architecture provides a massive advantage. The network can generalize expected values across similar continuous states. If it learns that a specific action is valuable in one location, it immediately infers that it might be valuable in a mathematically similar location, without needing to visit every exact coordinate. Deep Q networks solve the state space dimensionality crisis, but routing dynamic programming updates through a neural network creates a catastrophic new instability. Standard supervised neural networks rely on a core assumption. All training data must be drawn independently from a static, randomized distribution. The data cannot be sequential. But reinforcement learning violates this assumption through temporal correlation. An agent navigating an environment generates highly sequential data. If a robot spends 12 hours navigating a dark maze, all of its recent data is correlated exclusively to dark, narrow corridors. When it suddenly enters a bright room, the neural network aggressively optimizes for the new, completely different data. Because the inputs are temporally correlated, the network rapidly overwrites and erases the precise value functions of learned from the previous distinct environment. This instability is formally known as catastrophic forgetting. To prevent the agent from destroying its own memory, engineers introduce a critical architectural fix, the experience replay buffer. Instead of training the network instantly on every new step, the system maintains a sliding window of recent experience tuples. It stores the state, action, reward, and next state as a historical dataset. During training, the algorithm reaches into this buffer and randomly samples scattered batches of past experiences. Randomly sampling from the replay buffer breaks the temporal correlation of the incoming data. By shuffling its own history, the agent tricks the neural network into learning stably, processing the temporal feed as if it were a standard randomized supervised dataset. We now have the components to assemble a complete, robust system. By combining neural network function approximation with a stabilized data buffer, we get the fitted Q-learning algorithm. This diagram maps the complete modern architecture. In the first phase, an epsilon-greedy agent interacts directly with the environment, executing its policy to gather new batches of temporal data. Instead of updating the network immediately, these incoming batches merge continuously into the overall experience replay buffer, expanding the agent's historical record. Periodically, the system explicitly pauses the interaction loop. It locks the dataset, samples from the buffer, and runs supervised neural network training on the stored randomized dataset. This is the crucial design choice that makes the system stable. The architecture explicitly isolates the dynamic programming phase, gathering the data, from the function approximation phase, where the neural network actually trains. We started with a basic loop, measuring immediate rewards. We mapped updates onto tabular grids, hit a computational wall, and replaced the tables with deep neural networks, stabilized by synthetic memory buffers. Modern reinforcement learning requires more than a mathematical formula to maximize a reward. It demands an architecture capable of gathering data, stabilizing itself, and surviving the chaotic, continuous flow of temporal reality.